Hello and welcome to ISCW Lab Number 1. ISCW, that's Implementing Secure Converged Wide Area Networks. And most of these ISCW labs do revolve around securing the wide area networks. However, in this first ISCW lab, we're going to be focusing on a wide area network or a WAN technology, specifically MPLS, multi-protocol label switching. This is a WAN technology popular with service providers. And while there is cell mode MPLS and frame mode MPLS, the focus of this lab is on frame mode MPLS. The very first thing we want to do in this lab is to review MPLS. What is the theory of multi-protocol label switching? Then we will go out to our routers and enable MPLS on our interfaces. We will verify that MPLS configuration. Then we will make a tweak, an adjustment to our configuration dealing with MTU size, the maximum transmission unit size. As we review the theory of MPLS, we will discuss the potential need to adjust the MTU size to prevent fragmentation. But as we said, let's begin by reviewing the theory of MPLS, specifically frame mode MPLS. With frame mode MPLS, we still have a routing protocol. We happen to be using EIGRP in this lab that is going to determine out of what interface a frame should be forwarded. And the router is going to insert a 32-bit label, this MPLS label, between the layer 2 header, the frame header, and the layer 3 header, the IP header. As a result, sometimes we say that MPLS is a layer 2.5 technology because its label lives between layer 2 and layer 3. With this label, other MPLS routers inside of the service provider's cloud, they are going to be able to make forwarding decisions based not on a destination IP address, but rather on this label. This is going to make the forwarding of frames inside of the service provider's cloud much more efficient. Not only because we are avoiding an IP routing table lookup, but MPLS also offers us advantages such as traffic engineering. MPLS also supports QoS, quality of service, and MPLS is also very well suited for VPNs, virtual private networks, which can add security to an MPLS network. But in this lab, we're going to keep the MPLS configuration fairly basic. So for our purposes, just understand that we're going to be adding this label between layers 2 and 3, and the router is going to transmit that labeled frame. And to better understand the operation of MPLS, consider the two different planes of operation that make up the MPLS architecture. First of all, there is the control plane. The control plane associates a label with an IP route. In fact, when we go out to the routers in a few moments, you will see that every IP prefix in our routing table has a label associated with it. That operation is performed by the control plane. And the control plane is also running the protocol that does the label distribution. We are going to be using LDP, the Label Distribution Protocol, as that protocol. And thanks to LDP, we can then populate the LFIB, the Label Forwarding Information Base. You may have heard of CEF, Cisco Express Forwarding, which maintains a couple of tables, an adjacency table with layer 2 information, and a FIB, a forwarding information base with layer 3 forwarding information. Well, this LFIB is very similar to a CEF FIB table. In fact, CEF is going to be required in order to use MPLS. This LFIB, it resides at the data plane, and the data plane maintains this LFIB and forwards frames out of appropriate interfaces based on the labels contained inside of those frames. Consider a sample MPLS network. First of all, inside of the MPLS domain, we have an LSR, a label switch router. A label switch router is responsible for swapping labels. One label comes in, that label gets swapped out and replaced with a different label. Also notice, sitting at the boundary of the MPLS domain, we have edge LSRs. An edge LSR can, for example, take a look at the destination IP address inside of a packet and insert an appropriate label based on that destination IP prefix. This can happen when a packet comes into an MPLS domain. Then, at the other side of the MPLS domain is we're exiting the MPLS domain and we're leaving via an edge LSR. That edge LSR can remove the MPLS label. Let's walk through an example. Let's say that a packet with a destination IP address of 1.1.1.1 came into this edge LSR. The edge LSR could then label this frame. Perhaps it gives it a label of 10. It flows into an LSR, a label switch router, which is contained within the MPLS domain, and that LSR does label swapping. Maybe the packet came in with a label of 10, and it exits with a label of 20. Then the packet reaches another edge LSR as it prepares to exit the MPLS domain. This edge LSR takes away the label, and the packet gets forwarded out to the network just as it came in to this MPLS domain, with a destination IP address of 1.1.1.1. Let's take a look at the topology we're going to be working with in this lab. We are going to be configuring two routers, the HQ, the headquarters router, and the branch router. The SP, the service provider router, has already been configured for us. And in this lab, we are saying that our network has become an extension of our service provider's MPLS network. In other words, what we will want to do is to configure frame mode MPLS on our routers. In order to do that, we will want to make sure that CEF, Cisco Express Forwarding, is enabled. We will want to enable MPLS on our interfaces. Then we select what protocol we are going to be using for label distribution. We have an option. We can use LDP, the label distribution protocol, TDP, the tag distribution protocol, or we could use both. In our lab, we're going to select LDP, the label distribution protocol. Something else we may want to do is adjust the MTU size, the maximum transmission unit size of a frame. The reason being, since we are adding information such as a label, our frame could grow so large that it becomes fragmented by an interface. If we want to prevent that from happening, we might want to make the MTU size greater than 1500 bytes, which is the default setting. Since an MPLS header is 32 bits in size, that's 4 bytes, if we're just using a pure MPLS in our environment, we might want to increase the MTU size from 1500 bytes to 1504 bytes. Or if we are using an MPLS VPN, we probably want to set the maximum transmission unit size to 1508 bytes. Or maybe we're using an MPLS VPN with traffic engineering. In that case, we might want to use an MTU size of 1512 bytes. That's what we're going to be doing in this lab. Let's check out the syntax we'll be using. First up, in global configuration mode, we want to enable IPsef, Cisco Express Forwarding, for the router. We do that with the command IP space CEF. Then we go into interface configuration mode and enable MPLS label switching on that interface with the command MPLS IP. Next, we select the label distribution protocol that we're going to be using. In this lab, we will say MPLS label protocol LDP. That's the label distribution protocol. However, another option is TDP, the tag distribution protocol. Or we could use both. But in this lab, we are going to use LDP. And finally, we talked about the importance of having an appropriate MTU size. Since we are adding additional label information, if we want to prevent fragmentation, we could optionally increase the MTU size. And we said in this lab, we're going to be using an MTU size of 1512 bytes. Let's now go out to our routers and set this up. Let's begin our configuration on the HQ router. First, we go into global configuration mode and we turn on Cisco Express Forwarding with the command IPsef, CEF. Next, let's go into an interface Fast Ethernet 0/0, and enable MPLS on this interface. We can enable label switching on this interface with the command MPLS IP. We also need to select our label distribution protocol. We have an option. Let's say MPLS label protocol, and we can select either LDP, the label distribution protocol, or we could select TDP, the tag distribution protocol, or we could select both. In our lab, let's use LDP. With this, we are now done with the configuration on the HQ router. The way I'm accessing these routers is via an access server, so you may see the prompt change as we move over to the branch router. We are now sitting on the branch router, and we need to give a similar configuration here. Again, we go back into global configuration mode. We want to enable IPsec globally on this router, and we have a couple of interfaces on which we want to enable MPLS. First, let's go into interface configuration mode for interface fast Ethernet 0/0. Then we give the same commands that we did back on the HQ router. We say MPLS IP followed by the command to turn on LDP. We say MPLS label protocol LDP, and notice what happened on screen just then. We had a neighborship form. An LDP neighborship was formed between the branch router and the HQ router. We have one other interface to do on the branch router. We are connected to our service provider via interface serial 0/0/0. Let's give the same commands. Let's enable tag switching with the command MPLS IP, and then we follow that up with MPLS label protocol LDP. At this point, we have completed our configuration on the branch router, and we see another LDP neighbor change. We have formed an LDP neighborship with the service provider's router. That's great news. Let's give some verification commands now. On the branch router, let's give the command show MPLS interfaces to see which interfaces are enabled for MPLS. And here we see fast Ethernet 0/0 as well as serial 0/0/0 are enabled for MPLS. We may also want to see if we have formed any neighborships. We can say show MPLS LDP neighbor, and we can see that we have two LDP neighbors. We see their peer identities. 10.1.1.1, that's the HQ router, and also 10.10.10.10, that's the service provider's router. Specifically, that's the loopback interface on the service provider's router. And something interesting about MPLS that we can see with the show MPLS LDP bindings command is all of our IP prefixes have a tag associated with them. For example, 10.1.2.0, that prefix has a tag of 17 associated with it. We have other tags, 16, 18. That's what MPLS makes its forwarding decisions based upon, the tags as opposed to the IP prefix. In fact, we can even see these tags appearing in something like a trace route output. On the HQ router, let's do a trace route to 10.10.10.10, and we see as part of the trace route output, an MPLS label is appearing. You notice that? MPLS label 16. We are associating a label with this prefix, with this next hop address as part of the trace route. And something that we mentioned would be a good practice for the real world was to change the maximum transmission unit size, because we have MPLS overhead, we have VPN overhead potentially, traffic engineering overhead. Let's go into interface fast Ethernet 0/0 and set the maximum transmission unit size for MPLS to 1512 bytes to accommodate for that extra overhead. We then go over to our branch router and do a similar configuration. Let's get moved over to the branch router off of our access server. And once connected to the branch router, we go into interface configuration mode for interface fast Ethernet 0/0, and we give that same command, MPLS MTU 1512. Let's do it for the other interface while we're here. Interface serial 0/0/0, we again say MPLS MTU 1512. And I do believe at this point we have completed the goals we had for this lab, but as a best practice for the real world as well as the exam environment, it's a great idea to copy our running configuration to our startup configuration. Let's give the command copy running -config space startup -config. We've done this for the branch router. Let's jump over to the HQ router and do the same thing there. Let's do a copy running config to startup config. We can abbreviate that as copy run star. Let's now review what we have done in this lab. In iscw lab number 1, we examined the configuration of frame mode MPLS. MPLS, that's multi-protocol label switching, a very popular WAN technology with service providers. We began by reviewing some of the theory around MPLS. We saw how to enable MPLS on an interface. We then verified that MPLS configuration, and we could see our MPLS neighbors in the network. We then illustrated a best practice of configuring the MTU, the maximum transmission unit size, to accommodate for extra information that might get added as part of the MPLS process. For example, in our lab, we specified an MTU size of 1512 bytes. This would accommodate the 4-byte MPLS header, in addition to overhead added by MPLS VPN and traffic engineering configurations. And we reminded you of a best practice for the exam environment as well as the real world, and that is, after we are done with our configuration, we want to copy our running configuration to the startup configuration.